So I've made some slides for you, but obviously today is and Wednesday is for you guys, so feel free to derail me at any point. This is just what I came up with, but feel free to ask me any questions that you have, because like my job is to give you what you need for the exam. All right. So yeah, feel free to interrupt me at any point, but if you don't, I'll just keep going through these slides. Okay. So that's my plan, and yeah, I've tried to split up the final review into like non-programming stuff and then programming stuff. So let's do the non-programming stuff first, because you're going to have an essay, right, to write during the test, and you can put some information that might help you on the essay on your cheat sheet as well, right? So let's talk about our ethical theories, right? Let's review all those things. It's been a while. What do they have to offer us? So yeah, the first one is Kantianism, named after Immanuel Kant, very famous man. And ethics, just in general, is the study of what is good, what is right, what gives us pleasure, what should we do when faced with a dilemma. Okay, so ethics is just like the study of what's good, and remember that there's no right answer. So as long as you explain yourself well, argue your points well, you'll get credit as usual. So yeah, what Kant thought was he liked that golden rule, like act in a way you'd want everybody else to always act. And the word always was key, right? When he asks a question like, all right, should I steal? Should people steal? He'd ask the question like, all right, should everyone always be allowed to steal? And the answer is, Kant would for sure say no, right? There's no way that would ever be a good society to live in, first of all, because I'd be worried about my things all the time. And then, like, a huge thing of Kantianism and utilitarianism is that there's no such thing as like an exception just for you. No special exceptions. So with Kantianism, if you've decided that like, all right, I never want anyone to ever steal from me, that means you can never ever steal, even if you have a really good reason to. Right? Like to feed your family if you have no money at all. So if you were a Kantianist and you were dying and your family was dying of starvation, you would not steal any food. Right? So that's probably something that we would end up doing, right? We'd probably end up stealing as humans. But to a Kantianist, that would be an exception just for myself, and that is not allowed. All right. So there's that, and then also Kant tried to explain the golden rule idea in like this way as well. They don't treat people as a means to an end. Like they're all humans. They have their own goals. I don't want to just use somebody. I want to like respect them. Right. So that is also a useful tenet of his theory. So yeah, we talked about stealing. Also, lying is a good example, right? Well, would you lie? Kant would ask the question like, all right, should everyone always lie? Like, I never know if anyone I would never know if anyone's telling the truth. Is that a good thing or not? Would I want people to be able to lie to me all the time? He'd for sure say no. But then, of course, Kantianism breaks down sometimes. Sometimes we want to lie. But again, to somebody who is a proponent of Kantianism, they'd be like, nope, no special exceptions for me. I will never lie, even if it's like a murderer that comes to my house looking for my friend. I will tell that murderer where my friend is. Okay? That's what Kantianism is all about. It's just a rule is a rule. You got to follow that rule. Because in theory, the murderer would also, I don't know, maybe be a better person in that society if the murderer was also a Kantian person, because then you would never murder, right? Because no one would ever want to murder in that kind of society. So yeah, so Kantianism kind of breaks down sometimes when you think about it, but that's why it's a theory, not a practice, right? It should influence your ideas, but not like drive your ideas. It's firepower towards your essays. All right, so there's that, and then we just talked about stealing, right? Kantianism would ask the question like, should everyone always steal? Should I wake up every morning and wonder if I'm going to have like my car still? Probably not, right? In a Kantian society, no one would ever steal, which is maybe a good thing. I don't know. Maybe everybody should be Kantian. We'll have to have an experiment, right? So that is Kantianism in a nutshell. Just remember the word always, I think, would be the way to explain it. Any questions about that? You remember it? You can never forget it now. So there's that one. And then we got utilitarianism. That one was kind of the flip side. It's where the means don't have, or the end doesn't have to justify the means. something like that. So in utilitarianism, you are trying to maximize utility, right? It's part of the name. Maximize utility for everybody. Utility, happiness, pleasure for everybody, for this action that you're trying to consider doing, okay? And again, there's no special exceptions. You have to like weigh everybody's happiness, the universe's happiness, versus where in the universe where you do the thing, weigh the happiness of the universe, and the universe where you don't do the thing, weigh the happiness of the universe, and whichever one weighs more, you do. Okay, you either do it or you don't do it. So it's utility, happiness for everybody, for everyone, not just you, because the world does not revolve around you, even in utilitarianism, not just yourself. Okay, so yeah, if you have like two competing options, like either I do the thing or I don't do the thing, or like I can do the thing X or thing Y, you got to like pick out all the things, all the pros and all the cons, write them all down. Like, okay, it X produces that much pleasure in the world, in the universe, and then Y produces this much pleasure, utility, happiness in the universe, and then maybe Y ends up weighing more after you've like weighed the con. The cons are like gonna outweigh the pros. Maybe sometimes you have to like scratch things off, but it is a weighing game at the end of the day. Okay, so there's that, and it's all about consequences. Like what happens? What happens if I were to do this thing? Like the butterfly effect. What is going to go on in the world? Is this going to influence somebody else to like act in a bad way and like drive down total happiness? Like you have to try to predict the future, which makes it a little hard to like figure this out. Like it's hard to weigh things because you can't predict the future, but still, you try your best, and that's what utilitarianism is all about. All right, so you're trying to maximize utility for everyone, the entire universe, all at once. All right, so you don't mean much if you're trying to do something that is very selfish and good for you, influences and like increases your utility, but it ruins a couple other people's utility. Then you don't do the thing. Right? That's what utilitarianism is all about. Okay, is that coming back to us? So yeah, just remember that. And then another good example for this one is murdering. All right, so like the trolley problem. Would you kill one person? Would you flip the switch on the tracks? Would you kill one person when it means that you would end up saving 50 people? Like you have an option. Do you step in? Like do you have blood on your hands? Do you step in and do you save 50 people at the expense of one? And to a utilitarian, that would be a no-brainer, right? They'd be like, all right, yeah, sure, I'll flip the switch. I will save 50 people. I will murder one person. I will have blood on my hands because that would increase total utility, right? For the most people, because all those 50 people have families. That one person sure had a family, but 50 families being happy is better than one family being happy and 50 being sad, right? So you consider that. But again, the butterfly effect is really hard to like figure out. Like, what if that one person, like we said when I first introduced this, like what if that one person was like on the verge of curing cancer, something like that? We don't know. You'd have to do your best. Okay, it's hard to judge, but again, it's a thought experiment. All right, it's going to help you with your essays and hopefully your actions in real life. You weigh these. You think about these ideas before you do something important. Okay. So yeah, that's utilitarianism in a nutshell. Are there any questions about that? Is it coming back? Yeah. So yeah, just think about the keywords as you're thinking up how to assign space to your cheat sheet. Maybe you'll have a little tiny section for utilitarianism and Kantianism. So all right. The last piece of the non-programming stuff I want to talk about is probably fallacies. That was another key thing that we talked about. You had a long essay about it. We might as well go over those one last time, and then everything else you can just go back to the old slides for. So yeah, let's talk about fallacy. So a fallacy is when you're making an argument, or somebody else is making an argument, and there's an error, right? Somebody messes up. Either you do if it's your argument, or they do if it's their argument. It's an error in your reasoning. Right? So, but there is an argument going on because you're trying to convince somebody of something, probably. So, when there is a fallacy, it just means the entire argument is dead. It does not hold any weight anymore. You have messed up, or the person who has the fallacy in their argument has messed up, and the argument does not make sense anymore. right? It is not something that you should even think about and consider, right? You have to tell the person, point out to them, tell them to rephrase because they messed up, all right? So yeah, just think about like Thanksgiving dinner debates. I know that's a common thing, right, with distant family relatives. Fallacies flying around the table all the time, right? So think of it that way, probably. Do remember, though, that you can't just say fallacy. Okay, yeah, this argument has a fallacy. They messed up. Their argument is wrong. Turn in your essay. Every fallacy has a name, right? Remember that there are different names to every kind of fallacy, and I want you to be able to pick out which kind, right? There's a few different kinds that we talked about in the slides, and then there's a huge Wikipedia page of them. There's plenty of fallacies. I don't want you to memorize all of them, but remember that they all have names. Like you got false dilemma, you got straw man, you've got all these different things, right? All these different kinds of genetic fallacy, all these different kinds of fallacies, and they all have names so that like everybody can agree, like, oh yeah, I do agree with you. That is a straw man fallacy. Okay, you need to be able to point it out and analyze it because we care about analysis. Okay, so yeah, we got a bunch of different kinds. You can go back to the slides or back to your essay if you want to go review those. But I found some silly memes, and they're good examples of 3 fallacies. So I'll give you 3 fallacy examples so you can go back to the slides for the rest. Okay, here, 3 fallacies that I found in meme form on the internet. All right, so let's talk about them. So, okay, the first one on the left is a false dilemma fallacy. All right, false dilemma is when somebody makes the illusion, right, that you have 2 options, and those are all you get, right? You got 2 options total, that's all you get, but secretly, there's probably more than that, all right? So a false dilemma fallacy is like, all right, you can choose between thing 1 or thing 2, and that's it. Sometimes you do only have 2 choices, in which case it's not a false dilemma, but a lot of the time, there's a gray area, there's a secret 3rd option, or 4th or 5th, and so hidden away, there's this one, all right? So that's what a false dilemma is all about. Somebody's making the illusion that you only have 2 choices when really there's more, okay? It's also called the black and white fallacy. It's like you can choose black or choose white, but really there's some gray, okay? So that's what false dilemma is all about. So the second this happens, it's an invalid argument, remember. All right? So this is my silly meme that I found. It's like, all right, will you press the button? Because if you press the button, you get $50,000, but the person you hate the most gets double that, right? And then the meme is like, me, I hate myself, so I'm going to get $150,000, right? So that's hilarious, and I love it. That's a great example, right, of false dilemma, because what it's implying, right, is like either you have these 2 choices, like either you press the button, and this happens, right, either you get $50,000 and somebody else gets more, or you don't get any money at all, right? Somebody else you don't like gets more, or you don't get any money. When in reality, if you hate yourself, you get all the money in total, right? You're very rich, but not rich in happiness, okay? So does that make sense why that's false dilemma? That's how I would describe it anyway. There's probably another fallacy in this meme. I don't know. If you memorize the Wikipedia page, there's probably plenty, but just remember that they all have names. You just say it's a fallacy and move on. You gotta give the name of the fallacy, analyze it, tell me why it's the one you think it is, okay? So yeah, there's that one. Yeah, I just got a bunch of options. Feel free, again, to stop me at any point. Today is for you guys, so you can derail me as much as you'd like. Whatever you want to talk about, we can talk about. So yeah, the next one is strawman. The strawman fallacy is when like somebody is trying to build up, let's say that it's to you. Somebody's trying to knock down your argument, but they don't want to do too much work, and so they're going to pretend that your argument is made of straw, all right? They're going to pretend that you're saying something that you're really not. They're putting words in your mouth. That's the key, right? Strawman is when somebody's putting words in your mouth, and they're trying to say that your argument is something when it's really not that. It's more complicated than that, all right? And so they're trying to turn your argument into something made of straw that's easy to knock down, when in reality, maybe your argument was a good one, right? They're trying to pretend that you're saying something else when that's not what you're actually talking about, okay? So that's what strawman's all about. And so here is a silly meme example of a strawman fallacy. So it's like coronavirus. Back in the height of the pandemic, it was like Austria bans all gatherings of more than 5 people, and then it's like the meme is, all right, if you're a family of 6, that means you have to kill somebody, right? or send them off away from you. And so that is a straw man fallacy, right? Because you can imagine that this rule on gatherings had nothing to do with family, right? It's a silly example because nobody's going to think that this is true, but it's still a straw man fallacy if you were to pretend that somebody really meant this, right? It's like, this is such a bad ban. We should not have a ban like this because now we have to split up families even. And you see that's just putting words into the Austrian government's mouth, right? Because I'm sure that the rule was like, gathering means a bunch of people who are outside of different, like part of different households getting together, right? Concerts and things like that. That's what they're banning. Like, a gathering is not a household, a bunch of people already living together, right? That's not something you can ever disallow. And so, yeah, that's pretty much what a straw man fallacy is all about. Like, somebody saying this, or somebody imagining this, like, all right, this is what needs to happen to a family that's bigger than 5. You got to kick somebody out. When in reality, that's not really what was talked about in the law, right? They're trying to prop up the law as like a little straw man and bash it down, when in reality, like, it was a good argument, right, for people outside of households to not be getting together during the pandemic. Okay, so yeah, does that make sense? That kind of analysis? You'd say something like that, and you'd say it's straw man. Like, here's why. They're putting words in the Austrian government's mouth. They had nothing to do with family members and households, just about gatherings of different people. Therefore, bad argument. All right, bad meme argument. Okay, so yeah, if that one makes sense. I have one last example, and this one's nice and fun, right? So, tu quoque, remember, was a Latin term. Oops. This was Latin for the phrase "you too," right? You too, or you also. So, you know, the you from like Spanish or something, or French. So it's just, when you have a tu quoque fallacy, it's like somebody turning back around the argument on you. So like, I don't know, you're criticizing somebody for something that they did, and then they're criticizing you back. Instead of accepting your criticism as valid, they're criticizing you back because they're saying like, oh no, you did this bad thing too that you're criticizing me for. What right do you have to criticize me? That's kind of what a tu quoque fallacy is about. And so this is the good meme example, right? It's like, no, you turn something back around on a person, when in reality, maybe that criticism was still valid. Even if they're being hypocritical, they're saying like, this is a bad thing, you shouldn't have done this thing, when they themselves have done it in the past. Maybe that means they learned from that mistake, right? They're noticing that you're making the same mistake they did. Or yeah, exactly. Sorry, the perspectives have just been shifted in my mind. So like, you're noticing that like, when you're criticizing somebody and they're like, no, you did it too. Well, maybe you learned from that experience and you're trying to get them to not mess up like you did, right? So that's why the tu quoque fallacy is a bad one. It's okay to be a hypocrite because maybe you learn from your problems, all right? It's okay to have done the thing in the past and try to get somebody else to not do it, all right? So that's one of those do as I say, not as I do moments, which is technically, if you're to respond to that and say that no, that doesn't make any sense, I don't believe you because you did this thing too, that is technically a fallacy, right? Because maybe they learned from their mistake and they're trying to get you to not make that mistake. Okay, remember that one? Coming back to us. Questions about it? Because yeah, there's a million non-programming things that we could talk about, but these are like the keys, right? If you have an essay that I will ask you on the final, I think that these are 3 strong things to consider. You can go back to the slides for other like examples of things that we talked about, though. All right, so that's pretty much all the non-programming stuff I want to talk about. Right, so maybe have some spots on your cheat sheet for these kind of things. Write down some common fallacies. Maybe that would help you. Wink, wink. Something like that. All right. But yeah, that's all the non-programming things I want to talk about. Is there anything that is non-programming that you would like me to talk about? Because there's plenty of time. Because what I would do next is go to Python and start reviewing Python, because I will also be asking you Python questions. But if there's something that's not about Python that you're wondering about, that you're confused about, we can clear it up right now. Yeah, take a second. I'll have a drink of water for you to think about this, and then I will continue. If we're good. right, we good? Question, yeah.
Will any of the valid and sound argument things in those topics?
Oh, that's a good question. Yeah, we can go back to that. I think that's fair game for sure. We talked about it, but yeah, let's take a look. Which lecture was that? Was it maybe that one? Let me double check on my other computer just to save us some time. But yeah, that's a great thing. I don't think I can say that I'm not going to force you to like. I don't think in your essay I'm going to force you to use those terms, but they might help you to know them. So it is good to have them in your minds. All right, I'm not going to force you to remember exactly what they mean, but it could be like part of something that you'll bash down, like in your argument. So I think that would be helpful. I think, yeah, it was this one. Let's go back to it. Yeah, validity and soundness. So where were the actual definitions? We got dun, dun, dun. So they're part of deductive arguments. Remember the deductive arguments, like you got a bunch of things, firepower, right? Hypotheses, and you're trying to use them to imply your conclusion, right? And then validity and soundness were all about like how can we describe good versions of deductive arguments? Yeah. So a deductive argument, we said it was valid if these premises, they always give us the conclusion. We always have a way to get from these guys, combine them in some way to get to the conclusion. Thinking about it backwards, the definition thinks about it backwards. Like it's impossible for these to be true and this to be false. If these are true, it must always give us the conclusion. That's what it means to have a valid argument. Right? So it's like you can always like, this is A implies B, and this is A. You can always plug in the A, get out the B, which is your conclusion. Something like that. And then sound is like, sometimes in a valid argument, like, yes, if pigs could fly and the sky is green, then, I don't know, grass is blue. Like, maybe that works out in that kind of universe, but those two premises, like, pigs can't fly, right? So sometimes you have a valid argument, but it's not sound, right? A sound argument is one that's valid first, and then the premises are actually true in our current universe. Remember that? Those are those. Yeah, do you want to go over like examples maybe? Would that help? Like one of our examples from class, just to remind ourselves about like, what was the difference? Yeah, so this one was a valid argument. Let's go over like a valid one, a sound one, and then we'll talk about one that wasn't. So this one was valid, remember, because it's like all birds can fly, bats are birds, therefore bats can fly. So this was valid because we were able to take these two, combine them in a certain way, right? Like plug bats in because like we're assuming bats are birds, and every bird can fly. Then all right, that means bats can fly, right? You see how that like kind of follows? You can get your conclusion from the premises, from your hypotheses. That's what it means to be valid. And then sound is like, are these true, right? Are these actual true statements in our universe? They're not. So this is not a sound argument, right? Because like, first of all, you got penguins. And then second of all, bats are mammals, surprisingly. You remember the difference now? Is that coming back to us? Yeah, what else? We had a sound argument was one that, cool, was one where like this all worked out. Like the premises implied the conclusion. And then also these were true things in our universe, true statements. It's like all mammals are warm-blooded animals, dolphins are mammals, assume those things, and then we're trying to conclude, therefore dolphins are warm-blooded animals. That for sure works out, right? Because like you can take dolphins, plug them into here, and get out that dolphins are warm-blooded, right? So that's first of all valid. It all implies each other. And then it's sound because yes, all mammals are warm-blooded animals, and yes, dolphins are mammals. Yeah. That's the difference between valid and sound, or just valid. And then sometimes it's neither. What's an easy example? Like this one's like, these two things, all snakes are reptiles, all lizards are reptiles, they have nothing to do with snakes being lizards. Like, it's like an arrow in one direction trying to go in the other direction. Right? Like you have, these two cannot be used as firepower to prove this. They give us nothing. Right? So yeah, I think it's kind of as much as I wanted, as I can think to say. Are there any questions about any of that? Like, does that make sense? So yeah, I don't think I'm not gonna force you to say the words valid or sound if you don't want to, but it might be helpful on your essay because maybe Usually, right, I'll give you like some sort of ethical dilemma or argument to think about, right? I'll have you write about. And so maybe parts of the argument might be invalid, might be unsound. Like you can use those words to pick apart maybe the thing that I give to you, right? So that's a great thought. And maybe something you want to write on your cheat sheet. Yeah, is that a good enough review of that? Questions about it? So yeah, again, thank you. Derail me as much as you guys would like. I am happy to like go off the rails. So yeah, if we're good, think of new things if you like while I'm talking about this. But I will start with Python stuff now. So I think today and next time we'll get through Python stuff. So here's some Python things. First of all, I have made a lovely cheat sheet for you, which you will have to copy, right? You'll have to hand write it if you want to use it, though. All right. So I've made you something that you could potentially write on your cheat sheet. So here I'll release today's lecture, but of course I still need to put like the slides and things. Some of these links won't work. Like there is no recording yet. The slides aren't up yet, but this cheat sheet link will work. All right. So you can click that one, and if you would like, I have made this. All right. So again, if you want this on your final cheat sheet, you'll have to handwrite it. But here is a nice template. All right. So I've made you some cute little diagrams to explain like what goes on in Python when you're doing an if statement, an if else statement, an if elif else statement. It gets a little complicated, right? I've done my best. What happens when you do loops? You got while loops and for loops, and then we also have functions. Right. So maybe these are some things you want to write down on your own cheat sheet. All right. So I tried to be nice and color code it for you to at least help you study. But yeah, so this is for you. All right. So you have this now. But yeah, I made that. And yeah, let's just get Python ready. Do you remember that I will be forcing you to use the big computers in this room as you take your final? And you are allowed to use idle, right? You're allowed to use idle. Can't go on the internet or anything other than like you're taking the test on Canvas, but you can open up idle and have it to help you as you're taking the test. So you can like try out your programs before you submit them into Canvas. Okay? So you get that, but you may want to practice installing it if you've forgotten how to do that, right? Because I assume it's like these computers have restarted since you last installed it, or maybe you've never installed it on these computers. So like remember to do that before you start the test, and maybe practice if you need to. But yeah, let's talk about some Python stuff. So let's just talk about like the basics of Python stuff that's not even on the cheat sheet yet. Like the stuff we need before we can get to an if statement, right? It's like we got variables, we got different types of things. So let's talk about those. So let's see. What kind of code do I want to do right now? So first of all, you got a bunch of different, when you type like a number into Python, it's like either you typed like 42 or you type 3.14. These are actually two different kinds of numbers as far as Python is concerned, right? The first one's an int, the second one is a float because it has a decimal. That's important to worry about and wonder about. So yeah, remember that all the different types, you'll have to go back to the slides for the full diagrams, but I like to think of types as like little clouds. Like what kinds of things live in each type? It's like for every int, the int type, it holds whole numbers only, right? Integers are whole numbers only, so like 0's an int, 1's an int, 42's an int, like negative 55 is an int, like negative numbers too. But like 3.14, that is not an int, right? That is a float. So the float type is numbers with decimal places, okay? So there's all those, all right? So remember that. Remember the difference. And let's see. Anything of any type you can shove into a variable, right? And the way to do that is you'd be like x equals whatever you want. So like x equals 42, that takes, it's always right to left. So it's going to take the 42 or like do any math that it needs to do if it's not 42 yet. So like maybe it's like 42 plus 7. Like it does the math and then it puts the final int answer into x. Okay, so like that creates a new box in memory and it holds 42. So that's an assignment statement, we call that. And that creates a variable or updates an existing variable, right? We got that. And here, let me make a file for today. What is the number of today's lecture? It is 30, apparently. So let me make a new file, and I'll save it. in a folder that you will have. I would like to save it on my desktop here. It was lecture 30. Boop. There's that. And I'll call this one Python stuff.py. Alright. So here, let's show some of this. So I can make a variable now. So I can be like x equals 42, and you can ask Python to like show you stuff with the print function, right? It's like print. If you want something shown to you on the screen, it's like you print, and then you say what you want printed. With the call to the print function, and then you say ren, and it prints our 42. Python knows about the types of things as well. Like you put a whole number into x, so the type of x we say is, there's a type function that gets that out. What is the type of x? Print that out, please, Python. That will give you the type of the variable, and that is an int, saying that, yes, that's an int. You can also just ask for, like, what's the type of 42 itself, which is what's in x. Same thing. That's an int. But the type of 3.14, that is a float, right? And so, let's see, there's that. What can you do, like, the type, when you have a type of something, you know that it's an int, you kind of know what you can do to it as well. Because, like, baked into Python is the idea of, like, all right, integers, I know how to add them, I know how to multiply them, I know how to divide them. Like, you can mess with them using the operations that you know and love, right? It's like, let's print out, like, you can do x plus 2, x times 2, x, double star is squared, right? Or it's to the power of, if I put it 2 years, like this is cubed, this is squared. So if you have a number like an int or a float, these kinds of operations exist on that thing, yeah, because it's a number. Python knows how to do number stuff with it. It's like these are all the values, and if you give commas to print, it just like space separates the things. So like it produces this answer, prints it out, produces this answer, 84, prints it out with spaces in between. So that's that. Like the fact that you have an int, it knows how to do these things. Yeah, so that's what it means. You can do math stuff on numbers. So you got those. You got also floats, right? Floats are pretty much the same as int, except you have decimal places as options now. So like you can make a variable that's like 3.14 or even like 3.0. The difference between just 3 and 3.0. The decimal, the existence of the decimal means that you have a float now, right? 3.14. Print y, and Python knows that there's a difference. Print the type of y. It's like that is a float. So there it is, 3.14 float. And you can still do number stuff, right? You can do all the same stuff that you did on ints because it's still a number. You can add to it. You can multiply, divide, take it to a power. Okay, that's what it means to be a float. It's like that. All that stuff exists. Yeah. There are other types that you can't do those things to, right? Like the string type. Like if y or like if x was equal to high, you can't add 2 to high, right? It doesn't exist. It doesn't make any sense. So, including if this was the string for you, is the text at that point. It has nothing to do with a number anymore, right? It's as if you put high there. Remember that? So, that's something to worry about and to think about. Yeah. Does this make enough sense so far? Please stop me at any point. This is all for you guys. Okay? Let's see here. So there's those. What else we got? We have types that are very simple. We got the bool type. That's the simplest type ever. It's a very, very tiny cloud. That one is where you put Boolean values, like results of comparisons, and it's either the answer is yes or the answer is no in Python. Right? It's either true or false with a capital T and a capital F. And those things are, so what do we do? Y equals 3.14. That was a float, right? We made that variable. You can make bool variables. The bool type is very small. All that lives in the bool type is something called true and something called false. And you have to somehow create those in your operations. You usually get them from like comparisons, like equality check, less than check. And you can also combine them. Like once you have a bool, what can you do to it? You can't add 2 bools, but you can like and them, right? You do the and operation. You can or them. If you have 2 of them, you can or them together with the or operation. You can flip the true to the false and the false to the true with the not operation, right? That all exists. That's the thing. That's what you can do to bools. It looks a little weird to make a variable that is a bool, but we've done that a few times because like what produces a bool is here. Let's scroll this up so everybody in the back can still see it. What produces like true? What produces false? Like comparisons, like is 42 less than 43, right? that is a true statement? The answer is yes, so Python evaluates that to yes. Is 43 less than 42? No, the answer is false. It's like you can do these and shove the answer into a variable if you want. Usually just go straight to like an if statement, but it is okay. It is okay to do it this way, right? Be like, all right, Boolean b1 equals, hey, is 33 less than 34? So this will evaluate to, it's got to be either true or false, right? Python will do the work. This will become true, right? And then you can use it. You can also just hard code things like, all right, this one's false to begin with, just like our is game over variable in Pong, right? It's like, is the game over or not? Not yet, false. It might become true later, right? Once you lose the game. So there's that. And then what can you do to a bool? Can't add them, can't like multiply them, but you can and them, you can or them, you can not them, negate them. There's some others. You can always print them out, of course. Print b1, print b2. Because remember, what's going into the variable is not the idea of 33 less than 34, it's the answer, right? Python does the work first before it creates the b1 variable. So b1 is holding true. It's legitimately holding true. Python's done the work. It's asked the question already. Right? b2 is holding false. Yeah, and you can print them out, true, false, there. And you can combine them, like print out the result of like anding them together. b1 anded with b2. Remember that it's going to be true anded with false. Remember that the answer for an and, a false ruins the day, right? The false just brings everybody down. So if there's a false anywhere, the final answer for the total answer, like true anded with false is false. But the or, if you or things together, it's like it's true if anybody's true. So if I print out the result of, hey, is b1 or with b2 true? The answer is true because it's like true ORed with false is true. So go back to the truth tables there if you need them. All right, that might be something helpful, like the truth table for and or not. It might be very helpful for you to write on your cheat sheet if you've forgotten them. Okay, like what happens for which things. So those are bools. Are we good with bools? Questions about that? So again, Python knows the type. Like I could print out like what is the type of true Python? It is legitimately a bool. All right, it knows. What else? So yeah, there's also strings. Str is what it's short for in Python. Short for string. It's just like a string of beads on a bracelet that have letters, right? It's a string of characters. As far as Python is concerned, anything between quotes, either single quotes or double quotes, is a str or a string. It's just text. You think about it as text, all right? And you can do different things with strings, right? So you can say like S1 equals, it's just text really. It's like hello world. So you can either do like you can do double quotes or single quotes. Python doesn't care. They're both strings of text. All right. Remember that also this is like I don't know S2 equals 42. This is still a str. This is not an int. I cannot do math on this. Remember that it's complicated. It's weird. But that's just text. The 4-character followed by the 2 characters as far as Python is concerned right now. Okay? It's not the same as a number. You can convert the types, but it's not the same as a number right now. All right? Python knows the difference. Like print the type of S1. S2 would be the same, right? They're both strs. Anything between quotes is a str. And then what can you do now with strs? You can use the plus on strs. You can do the star on strs, but it's not mathematical plus. It's not mathematical multiplication. What happens when you multiply 2 strings in Python? Or it's not 2 strings. It's a string times a number even. Like print S1 plus. You can add 2 strings. That's fine. You can do that, and that will compute a bigger string with more. It'll just like shove all the characters next to each other. Take all these characters, add them together. It creates this string, and then it prints that out. That's what the plus on strings does, right? Has nothing to do with what you would, it's not mathematical plus. There's no such thing, right, on text. But same with like S2. S2, you can do a multiplication on strs. You can take a str and multiply it by an int. S2 times 3 or something. But that's not going to multiply 42 the number times 3, is it? Because this is just text. It's 4 and 2. The 4-character, the 2 characters, the symbol, right? So it produces this, which is not at all the mathematical 42 times 3. Yes? Remember that? You got to convert the types. If you need to do int stuff, like take the stir because maybe you got it from the input function or something, and then you give it back. All right, so that's how you think about it. Does that make sense? Like that's what you can do to a stir. You got those, and then also there's a baked-in len function for strings. It tells you how long the string is, how many characters is in it. So you can ask for, hey, Python, what is the length of the string S1? It's able to tell that to you, and that's helpful for if you want to like go into parts of the string with indices, stuff like that. So apparently there's 13 characters in this string S1. 13 characters all the way from the H to the exclamation point. Okay? So yeah, that's what you can do. Remember that because the types are different, like the plus and the star, they're overloaded. They're different to the plus and the star for like numbers. Yeah, that's a key difference. Got to worry about the types in Python. Yeah, I think that's what I wanted to say. Still good? There's one last basic type I want to talk about, and that's lists. Are you ready for lists? Let's do it. So a list is when you have a bunch of things and you want them all at once. Like you want just one name for a bunch of things, and you use those square brackets to get them, right? Square brackets, and you put whatever you want. It doesn't have to be all of the same type even. Like it can be 2, 4, 6 high. You can totally do that. Just put whatever you want in a list in Python, and it's happy. And you can get at things, all right? So let's say we do this line, like L equals 2, 4, 6, 8. What that does is it creates this kind of thing in memory. It's like one big variable called L, but it's got a bunch of different pieces inside of it. It's got the 2, the 4, the 6, and the 8 separately, if you wanted them separately. But if you just say L by itself, you're getting the whole thing, you're passing it around, but you have the ability to get at the pieces. There are indices involved, right? You've got index 0, 1, 2, and 3. It always starts at 0, yes? You also have len, which would tell you that there's 4 things in it to know that you only go up to like 3. It's always len minus 1, right? You can do that. There's also negative indices. Remember that there's negative indices. You can get at things quickly that way as well. You're like, all right, if you want the last thing, you don't have to worry about the size. I mean, this index is always len of L minus 1 index. If you want to do like the positive or non-negative indices. But if you just want it quickly without doing len, you can just be like, this is also index negative 1. There's always 2 indices, one positive or one non-negative and one negative. So like your last index is also negative 1. This one's negative 2. This one's negative 3. I guess that would make this one negative 4. So it like goes that way. Just like this one, the positive ones or the non-negative ones start at 0 and go up. So you always have 2 valid indices for where you want things, but the normal indices start at 0. Right? It's always starting at 0. And again, once you have a list type, you can ask for its length. You can add together 2 lists because like stirs and lists are very similar, right? It's like, what is a stir but like a list of characters, more or less, a list of single characters. So yeah, you can do all those things. Here, let me make a list now. Boop. So it'll be like L, or well, I'll make maybe a couple lists. It'll be like L1 equals 5, 6, 7, 8, and 9. So a few lists. I'll make another ones in a second. But you can ask for like, what does L1 look like? You can print out the whole darn thing, and if you print that, it's like that's you giving the whole thing, all of these numbers all at once, because they're all packaged together inside of this thing called L1 now. They're all there at once. There's the whole thing, but you can also get out the pieces with the indices. Yeah. So let's say you wanted this 7. You want to print out the 7. So one of the indices, one of the ways to get to the 7 is like this is index 0, this is index 1, this is index 2 of the list. So if I go to L1 at index 2, remember the syntax is those brackets again. L1 at index 2, that would pick out the thing. There it is. There's my 7. All right, is that making sense? Coming back to it. So I can get pieces. You can also use that syntax to set pieces. Like, all right, L1 at index 2, I'd like that to change. You put that on the left side of an assignment. Like, all right, now make it 77. And that's now changed the index from 7 to 77. If you print L1 again, the whole thing's changed, right? Because you've changed that piece of it. That's my list now. Yeah? So you can go into pieces of it one at a time if you need to. All right? So there's that. You can always get at the length of your list. The len function exists. Print the length of L1. Tell you how many things are in it, how many elements. There's still 5, right? 1, 2, 3, 4, 5. 5 things, though they have changed since the start. And you can use that to get at, like, what is my last index? It's always your length minus 1. That must be index 4 now, right? And that checks out. 0, 1, 2, 3, 4. Or you can use the negatives. That's fine. So there's that one. You do have plus on lists as well. It creates a bigger list, just like plus on stirs makes a bigger stir. So like if I have another list, L2, that holds these things, think about what's going to happen if I say, all right, create, and then print L2 plus L1. Build that and then print it out. You see what's about to happen? What list is going to be made? As you might expect, it's going to like shove the things together. It's like, all right, first these things, build a list, a bigger list, right, with plus. That holds 1, 2, 3, 4 first, and then whatever was in L1 after that, 5, 6, 7, 8, 9. Or 5, 6, 70, 79, because I changed L1 there. Yeah, so that's important. So that's how that works. I think that's what I wanted to say there. So yeah, just remember the indices. You can use the starting at 0 indices. Those are probably the ones that you want to remember, but you also have the negative ones if you need them. It's a quicker way to get at like the right side of the thing. All right. So that's lists in a nutshell. Are there any questions about those? Still all right? Yeah. Again, just yell at me if you want to see more examples of something. I am happy to oblige. So there's that, and then the final thing on this slide is like, what if you want a program that's different when every time you run it? How do you get things from the user of your program, the person you give this to? So like if you make a game, how do you get back something from them? So like, all right, let's do the input function. Input is the name of a baked-in function to Python that what it takes one argument. You give it the thing that you want to display to the user, the prompt that you want to display to the user while the program is waiting for them to give you something. And then they're going to see that, they're going to type, and then they're going to press enter, right? They're going to press enter, and then input gives you back whatever they typed after it returns it to you, right? It gives you back whatever they typed, the user typed to you, and you can save that away, usually. You're going to want to save that somewhere. And do remember, though, every time you use input, you're getting the text of what the user gave you. So if they typed 4-2, you're getting back the text as a stir, right? The character 4, the character 2. It's your job to change that into an int if you want to do number stuff, right? Because maybe sometimes they're going to type a sentence. You're always going to get a string back. You're always getting a stir. So if you want to do number stuff and the user, like you bank on the user giving you a number, you better convert that stir to a number. This is not yet a number, all right? So let's do that all in one fell swoop. So here, let's talk about that. So let's say we would like the user we'd like to ask the user their favorite number, right? Like enter, hey user, what is your favorite number? Is your favorite number? Question mark, and I'll leave a little space because this is what's going to be displayed to them as their type. If I leave a space, then that's like they're going to type after the space. And then this is going to result in whatever the user typed, so I better save away the answer, right? It's going to return back the answer to me. So I'll save it into like a variable called num, let's say, all right? And so after this is run, I'll get back something in num. We can print it out, print num. But the type is always going to be, if I print the type 2, it's always going to be a stir, even if the user types a number. So here, if I say, what's my favorite number? So input is running right now. It's waiting. It's on this line. It's like we can type and press enter, like 42, hit enter. So we get the 42, but the type of that thing is a stir, all right? So remember, what we can do to stir is like, it's like we got this, right? And that created like S2 times 3 was like 42, 42, 42. It was just the characters a bunch of times. It was not numerical at all, all right? I guess technically you could have done this like 1 is my favorite number. It's a stir, right? If you're getting characters with input. If you want to interpret those characters as something other than just text, then you got to convert the types, right? So remember that, because if you think that like num times 2 is going to do something normal right now, it will not. My favorite number is 42. Num times 2 right now, because it's a stir, it's holding the text 4 then 2, the character 4 then the character 2. It's gonna duplicate it, because that's what the star does. It just duplicates stirs. So yeah, if you want to do number stuff, what you do is you convert the types. You're like, all right, I would like to make the integer form of num. You think about what type you want, and you use it kind of like as a function. That is how you convert the types. Like I want an int out of whatever num was. So this call right here will convert and give back to you the integer version of num. If it really was an int, it will give you back the int form of it. Then I can save that right back into num if I want to. So this will do the conversion. This will give me back the new version, the updated numerical way, right? Num gets, like if it was 42, it was the characters 42, now the int, we get the actual number 42 that we can do math on, shoving that right back into num, and now it is an int, right? So if we do it that way, now num is an int. It is an integer. We can do things too. And this is kind of an art form because maybe like you don't know what the user gave you. Maybe their favorite number is pi. So like if you wanted that, if you wanted the option of getting numbers with decimal places, you want to convert it to a float, right? Those are the two different number types. You got to worry about that. But now at least num is an int, assuming the user is only going to type whole numbers. And now we can prove that. We can do math on it. Like num times 2 now is going to be a little bit different. So what's your favorite number? 42. So after we do this, this will convert the types. It's going to reset the num variable into, like here's kind of what we did. Like we had num, boop, and it held originally the string 42, the characters like that. But what we just did here is we converted num to an integer and then replaced whatever was in the num variable with that integer. So we did that. The real int is what's in there now. So that's what we did. And then the type is now an int. And it actually does math now. Now the star on ints, of course, does numerical multiplication. Okay. So I think that is what I wanted to say for that example. So that's input, converting types, because maybe you wanted something different than what you got. You don't just want the text, you want like to do math. Okay. So that I think is what I wanted to say for that. Any questions about this one? Still doing all right? All right, I got 3 more slides now. So let's talk about conditionals. Those are if, elifs, and elses. You don't have to use all of those because you have just ifs, right? Use just ifs if you need to. You can do if elses. You can do if, elif, elses. And you can have as many elifs as you need as well. It doesn't have to be just one. So let's talk about those. So yeah, you are going to ask a question of Python. Like these conditionals allow you to do the following. It's like, ask a question of Python, hey, is x less than 5 or something? Is x less than y? And the answer is either going to be yes, true, or no, false, right? And then you can do this, like do thing 1 if it's true, do thing 2 if it's false. That becomes an if else, right? That's how you think about that. Like you want to do one thing or another, right? And the way that you start is by asking a question that's either true or false, and it's comparisons that get you there, right? Those are all going to give you back true or false, and that's your answer, your final answer. And that lets you control, right? Control what you're doing based on your comparisons. So there's that. So if you want to do, for example, just a normal if statement, does either, bless you, one thing or nothing at all. So an if statement just by itself is like you give a condition, you give a body, remember to colon over, tab over, space over, do all that fun stuff. If you do it this way, what happens is it's going to ask your question. If the answer is yes, it runs the body. If the answer is no, it does nothing. And then the whole thing's done. Either it ran the body or it didn't, and then it goes straight to the after. So that's kind of how you can read this. Like either the condition is true, it runs the body, or the condition was false, it does nothing at all, just skips it. All right? So that's what I've tried to draw for you. And remember to do that. It's like if you give your condition something that's going to become true or false, you give your colon, then you tab over, your editor will do that for you, idle will do that for you, and then you give your body as many lines as you want indented that achieve your goal, right? And that's how that works. So let's do, I don't know, let's do a few examples. Let's do an example of, so that's just if, but usually, most of the time you want to do an if else. It's like, all right, if the thing is true, do one thing. If it's true, do one thing. If it's false, else, do the other thing. Only after doing one or the other, we're done. Just like go down this side or go down this side. So that's an if-else statement. Okay. So that's now let's do one thing or another. That's kind of this one. That's an if-else. Right. So let's do some silly examples. So here let's pretend we're in an amusement park ride. We'll ask the user to enter their height in like inches or something. We'll get their height and we'll see if they're tall enough to ride the ride. All right. That's a good question asking kind of program, right? So make a new file. I'll call it conditionals.py. We're doing things conditionally, right? There's that one. And so yeah, let's ask the user, hey, how tall are you? It's like, ask the user for their height. That's going to be an input, right? Input, hey user, enter your height in inches. Colon space so they have room to type it. So ask them to enter their height, and let's say that they're only going to they're not going to say I'm 47.5 inches. Let's just say that they're only going to give us whole numbers. So if I shove this into the height variable, it is not something I can do math on yet, right? It's just the characters. But I can immediately convert it if I want to. So take the result, take the stir, immediately give it to the int function to convert it to an int. Now height for sure holds a whole number, right? And then let's say that the I don't know, the amusement park ride's like, you got to be 48 inches. You got to be like 4 feet or something. So to ride the ride, so if your height, if your height, the height of the person, is less than 48, then what do? We tell them they can't go on the ride, right? It's like print, sorry, you can't go on the ride. Sad face. But otherwise, right, else, if this was not true, that means their height was like bigger or equal to 48. They were at least 48, right? So then you can print, hey, you can go on the ride. You can go on the ride. You're good to go, right? Happy face, right? Remember that stirs can be either double quotes or single quotes as long as you're consistent, right? So yeah, that's kind of like doing one thing or another. That's your if-else. If the condition is true, do this. If the condition is false, do that, right? Any questions about that one? Does this make any sense? What's about to happen here? If we ran it, in your height in inches, we got, I don't know, if it's 49, you can go on the ride. But if it's, I don't know, 42, sorry, you can't go on the ride. It's like it only does one or the other. And then once it's done, it continues with the rest. Like the whole thing's over at that point. So it's done one side or the other. It's never going to do both. Okay? So that's how that one works. What else? Yeah, so that's that one. We good? Because the more complicated one is an if else. It's like what that one's all about. You can have as many else as you need as well. It's always going to just try, like this is a complicated diagram. But if you think about it, what it's doing for an if else is like it's trying this first condition, and if that one checks out, if it's true, if it works out, then that's it. I've run the whole thing. So it's just going to find the first condition that works and run its body and be done. Right? So if this one's done, it's going to run this body, be done with the whole darn if else. Otherwise, if that's not true, read elif as otherwise, like it goes on to try this one. Otherwise, if that one's true, do this. Then it runs that one, and it's done with the whole thing. The first one that works, it runs the body. The first condition that works, it runs its body, and then it's done with the whole thing. All right? If it ever gets that, it's like, that was this one. Like, all right, that one. First one was false, all right, try this one. If it's true, okay, run the body, be done. Otherwise, if that's still false, you keep following through, right? But you can optionally have an else at the end. You don't have to have it, but if you want to, you can put an else here. And that one has no conditions. Like, that's your follow-through case. Like, if that one's not true, then, all right, do the body of the else, and then we're done with everything. Right? So it's just going to find what an if else does. You have as many elifs as you need in the middle as well. It does the first condition. It finds the first condition that works, that's true, runs its body. Okay? So a good example of that would be like a grade calculator. Like the user enters their grade, and we can like figure out what their grade is, A, B, C, D, or F. Yeah. So let's ask the user for their grade. Hey user, input, enter your grade as a percentage, right? Colon space. And this, your grade can probably have like, I have a 95.23 or something. That could be a float. So I don't want to convert it to an int, I want to convert it to a float, right? For sure it's not a stir. So I want to do number stuff. And then now, like, what is my grade? It depends, right? It's either what an if else kind of does. Like, it's all right, if it's true, it does this one. Otherwise, if it's false, it lets you try a bunch of options. Like, all right, otherwise, maybe check this one. If this is true, try this. If that's false, like if it's an A, print A. Otherwise, maybe it's a B, print B. Otherwise, I don't know, maybe it's a C, D, or F. Like, we gotta try all these options. Like, it's like a, I don't know, it's like a leaning little diagram like that. So that's how you think about it. It's like it's trying a bunch of things, one at a time. It's just trying the first comparison that works out. That's how you think about it. All right. So the diagram, just try to stare at the diagram. I think that will help as well. I tried to be helpful and color code things. But yeah, say we've got this grade from the user now, and we're like, all right, now let's figure out what their grade is. So it's either A, B, C, D, or F. So if, right, if the grade, you usually do it in order. It's the easiest way. If the grade is greater than or equal to 90, or 90.0 if you want to get fancy, right, because it's a float, then it's an A, right? You can print your A out. And it's okay for it to be above 100 because like there's extra credit, right? So there's that one. So if that checks out, like if it's greater than 90, it's done. It's going to print A, be done with the whole if else because I'm going to have more, right? I'm going to have more options. Like elif, maybe, otherwise, if that wasn't true, maybe it's a B, right? You haven't tried that one yet. Otherwise, if it wasn't this, if this was false, that means it's less than 90, but maybe it's greater than or equal to still 80. Do you see how if I get to here, then it's a B. If I get to this body, that means this was false because it would have run the first one if it was true. That one's false, and this one must have been true, right? If I get here, that means the second condition was true, but the first one was false. So it's greater than or equal to 80, but also less than 90. That's your B range, right? That's how you get it. And it's like, you just keep doing that. It finds the first one that works. LF, otherwise, maybe if that wasn't true, maybe it was greater than or equal to 70, right? It's going to find the first one that works. So you do want to go in order like this to make it easier on yourself. If that wasn't true, it's C, right? Because the only way we got here is like if this was not true, it wasn't an A, it wasn't a B. All right, if this is true now, that means it's greater than or equal to 70, and this one also fails before it. So it's less than 80, right? 79.999, as big as it could be. If otherwise, maybe it was greater than or equal to 60, print D. And then if none of those were true, right, you can have a fall through case of like an else. If none of that's true, none of those previous conditions ever hit, then else, it must have been smaller than 60, so it's just an F, right? So you can have a fall through case if you need to. You don't have to have one if you like it only goes to D or something. That's fine. You could have turned this into an LF as well. It's like LF grade is less than 60. That's the same thing if I spell grade right. There's no difference, but it's less typing. Like, all right, just if it wasn't true, my fall through case, it must have been an F. Does that make sense? It's kind of how you read that. It's going to do one or the other, right? It's going to find the first one that works. Read LF is like otherwise, and else is like otherwise I give up. .2. And your grade, let's be like 85 or something. So it's a B. It's like this one was false. It didn't do the A, but this one was true. So it found the first one that worked. Now it's done with the whole darn thing. All right, that's how that works. It doesn't try any others. It's always going down one path. One path only. Oops. I'd like to display it all, please. There you go. Like, no, 65. There's a D because it's like this is false. All right, otherwise try this one. Still false. Still false. 65. Still not greater than or equal to 70. But it is finally greater than or equal to 60. And so that's why it prints D. See that? That's how that works. And then if you give it like 55, it prints F because like none of these check out. These are all false, 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 false. Just like goes to the fall through case and prints F there. Okay? So that is LF. All right? If, LF, else. It's a big long bunch of chain of options. It just finds the first one that works. Questions about that one? All right. I want to do some loops now. All right. So we got different kinds of loops. I got a while loop and a for loop. The while loop is very similar to an if. It's like you got some stuff you set up, and it's like instead of checking a condition, running the body if it's true, it checks the condition, runs the body as long as it's true. It always comes back to rechecking the condition. That's what the while loop does. It lets you loop back around. It's like as long as this is true, I'll run the body and then keep coming back to check the condition because as long as it's true, I'm going to keep going. Once it becomes false, though, then I'm done. Then I go down to the rest of the code. All right? That's what a while loop is good about. Good for. Let's do those. A while loop. Let's do a few examples here. So here's a while loop. Boop, boop, boop. So save this. Loops.py. So let's make a loop that prints the numbers from 1 to 10. We'll do that. It's like, all right, how do we do that? It's like, all right, set it. What's our first number that we care about printing? Like 1, right? So start a variable. And it's like, as long as I is a number I care about printing, like it's less than or equal to 10, it's working its way up. Then what do I want to do with I? It's like print I, and then advance it, right? I equals I plus 1. Can we see that in our minds, what's about to happen? We're getting better at that. So just going to continuously run that body as long as this is true, as long as like, all right, it's 1, it's true, print it, and make it 2. Keep going. It keeps on making it bigger and bigger, right? So that's how that works. And we can draw a diagram if we're not ready for that yet. It's like, draw a diagram kind of how we want to have our code execute and loop back around. It's like we start a variable at 1, and just like as long as I is something I care about, as long as it's less than or equal to 10, what do I want to do with it? As long as that's true, I would like to print I, and then also increment I. Yeah, I want to do that, and then it just keep on wrapping back around as long as that's true about I, because It's 1 now, it's 2, it's 3, it's 4. It's still less than or equal to 10. Keep printing it, making it bigger. But the second it becomes 11, right, then we're done. We go to the rest of our code. I call that like after in my little diagram here. That's what we wanted, right? Once it's done, like once it's too big, I don't care about printing it anymore. Then I'm done with the whole loop. Does that make sense? That's kind of what we just did. So that's why we get our 1 to 10, and that was the code. Is that coming back to us? So there's that one. I don't know if I showed you this in actual class, but like here's something cool. You might need it one day. It's like if you ever wanted to stop your loop early, you can say break. Just say the line break to stop it. It's like maybe you don't like you have this, it went up to 10, but you only want it to go to 8, and you don't really know how to fix it very easily. I know you can change it pretty quickly, but like you can do this instead. Like if I is equal to 8, like you just made it, you printed 7, you made I 8, like you don't want to print the 8 maybe. You can say just break by itself. It's a keyword, and that stops early. Oh, sorry, I'm on the wrong line. Stop early with break. Just a line called break. And that will just like, all right, if it ever gets there, like I was 7, it printed 7, and then, all right, I is now 8. So if I is 8, it breaks and stops the entire loop. It quits early. That's one thing that's useful. So yeah, I think that's what I wanted to say for that one. Are we good with that example? It's like print from 1 to 10. Don't know if I can get through everything today, but we got more time next time. So there's that one. And then I also want to do like sum up all the values of numbers. Like let's say that the user is going to give us some stuff. Let's sum up all the numbers that they give us until they give us -1. Yeah. So let's say like I'm going to ask them each time in a loop repeatedly, like give me a number, 42, 43, 40. If they keep typing stuff that's not -1, I'll get it and add it. But the second they type -1, that means they're done. So that means they didn't really want -1. It means that's just like a marker to mean they're finished. So we'll output the sum of those numbers. So that will be my example. Right? The user's going to give us a bunch of numbers. -1 means they're done. Every number up until then, we're going to add into a sum variable. Okay? So that is something we can do, also with a while loop. So the very first thing, we need like to keep track of the actual sum eventually, right, into a variable. Keep track of the sum in a variable. So like I'll call it total or something. Starts at 0. I want to add into this total variable every new number I get from the user, right? Until they give me -1, at which point that means they're finished. So yeah, well, let's just get a number from the user. It's like, all right, what is my next number from the user? So that is like I can say input, hey user, enter the next number, or -1, right? Boop. Something like that, colon space, and yeah, let's say they're only going to type whole numbers, so we can do that one. And then just kind of forever until the end of time, as long as that number that the user's given me is not -1, right? I want to add that number that I got into my total. That's kind of how you think about it, yeah? Like as long as that number is one I care about summing, keep trucking, right? While next num is not equal to, exclamation point, not equal to -1. What do I want to do? Right? I want to repeatedly take that number that I got, next num, add next num into total. Like that's one I want to worry about, right? That's part of my answer now because it wasn't -1. As long as that's true, keep doing this. And then also, right, I want to repeatedly get another number, right? So inside the loop, get the next number as well. Get the next number. That's how you can think about it. It's like get the thing, as long as this number wasn't -1 that I got, something I care about remembering, add it into my total, and then also keep looping, right? Get ready for the next number. Maybe that one's -1. Maybe it's not. Keep going, right? So that, how do you fill that in? Total equals whatever it was plus that new number. And then also how to get the next number after that. You just kind of do this all over again. So there's probably a cleaner way, but like that's one way to do it. And so yeah, you kind of see how by the time this loop is done, then next num must have been -1. That will get us out of this loop, and then we'll be down here when we are here. When we get here, next num must be -1, right? Because otherwise it would have stayed in this loop, right? So if it is -1 now, that's why we're done. And that means the user's finished with giving us numbers, and we want to output the sum. Might as well print the thing that we were working so hard on. It's like, what is the sum? Sum colon and then a space with the total. All right. If I comma separate, I get a space separation. So yeah, that's kind of how that's going to work. So start total at 0. As long as I got a new number that's not -1, add it in, get the next one. So repeat that until this becomes false. What does it mean for this to become false? If it's not true, the next number is not equal to -1. That means it must have been equal to -1. That is what will stop us. So if I type my 42, 43, 44, 1, 2, 3, -1, apparently the sum of all those numbers is 135, and I trust that. So there's that one, and then we got, let's see here, it's like 1, 2, 3, -1. Like whenever you're done, it'll give you that sum. That is 6, right? Are there any questions about why this code is going to add up a bunch of numbers? It's going to stop when the user gives us -1. You can kind of see what's going on there. So yeah, loops are fun. They let you repeat stuff. So that's one kind of loop. That's a while loop. And then there's also, we got 5 minutes left. Let's see how much of this we can get through. We might have to like do more next time. But at least for now, we can do the first bit probably. Let's do let's at least introduce for loops. All right, we can get to the. I don't think we'll have time to finish all of this slide, but we'll do as much as we can. All right, we'll finish it next time. So this is what a for loop looks like. You say for, and you give like a variable name that's going to exist for the life of the loop, and then you say in for some variable name in, like a list thing. Think of it as a list. Run a body, right? And so what it's going to do is it's going to go through every element in your list, essentially. It's going to go through every element in your list from left to right. It's like as long as there's another one, it'll set that variable that you gave a name to here to that next thing, and then run the body of your code using that next value. It's like for every variable in the list, I want to do something. Essentially, that's what a for loop does. It helps you. You could use a while loop to do this, but and use indices, but this is like faster. As long as you have a new value in your list, keep on trucking and run the body on it with the variable being set to that new thing. And then otherwise, once it's finished, then it's done with the whole loop. That's kind of what a for loop is all about. It goes through your list. Like it iterates through something, and I want you to think of it as a list, at least in this class. There are other things that are like list-like ranges. The range function gives you back essentially a list. Like you can go through the list L from left to right, the 1, the 2, the 3. You can also go through a range of things. Remember that the range function kind of works like this. Range 50 gives you back essentially a list that starts at 0, 1, 2, all the way to 49. There's ways to start at 1. Like you can give it 2 arguments. But remember, it always goes up to 1 minus that last thing that you give it. So that's important. So yeah, let me show you. Might have time for one example. Let's make... let's do a minimum finding function, all right? Or not a function, but like an example. So let's go through a list and let's find the minimum of all the things that the user gives us, all right? So let's say that the user gave me a list, like they typed in a bunch of numbers, and they gave me the list 3, 1, 2 or something. To find the minimum of that list, like you got to save it. What you do is you make a guess, right? This is our strategy, all right? I'll just like set that. We'll probably have to wait until next time. I got only 3 minutes to talk about this. So what we do is we make a guess, like pretend that the first element of our list, guess that that's the minimum. We may be wrong, all right? A lot of the time we will be wrong. But then we're going to go through the rest of the list. We saw this guy, then we go through the rest of the list, the 1 and the 2, and then we have them fight for the spot of the min variable. If, we went through the 3 already, if the value that you see that you're trying to fight with the current min value, if it wins, right, you're just going to keep on updating our guess of the minimum as we see new elements. Now it's 1 versus 3. 1 wins. You're going to replace it. Replace 1 into min there, and then 2, you'll see 2 versus 1. 1 is still better, so 1 will stay there. So like you're going to loop through the list. 3 versus the 3, it doesn't change. 1 versus the 3, okay, 1's better. 2 versus the 1 is still best. And so by the time you get through the entire list, you will have put the right minimum as long as they fight properly, right? The true minimum will win out, yes. And so that's a good example of like wanting to go through a list and like checking things, right? So like we're going through a list from left to right, visiting all the values and having them mess with the minimum. Do you see how that's going to like turn into a for loop? We want to go through every value in that list, all right? So let's at least get started with that. Because because we're going to need a list of numbers. Let's like steal this code to get a bunch of numbers from the user. Oops. What have I done? There you go. Keep it, but make a new file, and then we'll write into this file next time. We'll actually do the thing. I'll make a file called forloops.py, and what we will do is let's make, instead of keeping track of a total, let's like have this build up a list. Let's start a list at emptiness, and then every time I get a new value, I'll add the next num into the list. And this will be a way to like build up some list the user wants to give me. Now it's list equals my list L equals the old list plus a list containing just that next num. And look at what's going to happen by the time I'm done with this. Print L. If I say in my for loops program, I haven't used the for loop yet. I say 4, 5, 6, and then -1. I have now put into L the list 4, 5, 6. This is going to be useful. Then I can like try my my minimum example on a bunch of different lists. But this is a way to build up a list. All right, so I'm getting new numbers from the user one at a time, and I'm building up. I'm adding in new elements into that list. All right, and then by the time I'm finished with that loop, I've got a list to use, and we'll go through this list next time to find the minimum. All right, I think that is officially all that we have time for today. We will come back to this slide on Wednesday and continue. All right. Any last questions about anything? You're allowed to leave now. This is the end of class time for sure. But if you have anything, stick around. I got office hours. No. Just to remember where we were. Okay.